So we ended talking about different fossil fuels and the carbon dioxide they release. This relates to our next topic of greenhouse gases, and I don't really want to explain them yet. So let's go ahead and dive in. So we talked about carbon dioxide entering our atmosphere. We're taking the carbon that's stuck in fossil fuels, and by burning it, we're turning that carbon into carbon dioxide and release that into the atmosphere. But why do we care? So what? So what if carbon dioxide is entering the atmosphere? Plants will take it up and it'll go into the ocean, so why do we care? And the reason we care, the reason there's so much hype around it, is that carbon dioxide is what we call a greenhouse gas. And you may have heard of this term before. So what is that though? In order to explain a greenhouse gas, I need to explain the greenhouse effect. The Earth is covered in an atmosphere, which is unique-ish to our planet. There are atmospheres on other planets, but our atmosphere is perfect, so to speak. It makes it so that here on Earth we're at the perfect temperature for life. So what happens is here's our Earth, and this kind of blue-green halo around it is representing our atmosphere. Our atmosphere is a lot smaller than this, though. So what happens is the sun releases energy, and that energy comes to us on Earth, comes to all the planets in our solar system. And that energy, it starts out as light energy, but it will turn into heat energy as it hits things. So this energy will go here into our atmosphere to warm up the atmosphere, and it'll hit Earth and warm up Earth. Two things can then happen. Some of that energy, some of that heat, warms Earth, and then it hits Earth, and think of it as a ricochet. It hits Earth and then wants to bounce back out into space and releases that heat into space. The other thing that can happen is when that energy goes to leave, goes on its way out to space, it can bounce back. It can hit something that then pushes that heat back to Earth. And that thing that it's hitting is a greenhouse gas. You think of, just gas as something that is, you can move it around, but gases hold in heat. So in this image, imagine there is, all these little molecules. These molecules representing a greenhouse gas, such as carbon dioxide. So this heat goes to leave, but it hits something, and it hits it, and it bounces that heat back to Earth. So that's the greenhouse effect. The reason it's called a greenhouse effect is this is very similar to how greenhouses work. Greenhouses grow plants no matter the time of year, and they have a special greenhouse glass. This glass allows light and heat to come in, and then when that heat goes to escape, if you have really bad windows, this might happen in your home. But a greenhouse glass is designed to have molecules in that glass that then bounce this heat back inside, which is how these greenhouses stay so warm year-round. That's exactly how Earth works. And this is incredibly important. The greenhouse effect is crucial. If we did not have the greenhouse effect, Earth would be way too cold. This heat that comes from the sun isn't enough. It's not enough to keep Earth warm enough. It would get way too dark when we're on the other side, when it's our nighttime. And so this greenhouse effect is incredibly important. But the problem is we're increasing the number of greenhouse gases. We're making this a lot thicker. A lot more greenhouse gases. So what happens is that instead of some of this heat escaping into space, more and more of it is getting trapped. Our greenhouses, or the greenhouse glass, so to speak, is getting thicker. It's keeping more of that heat in instead of letting some of it escape. I also think about this like a sweater. You put a sweater on, your body radiates heat, but that sweater keeps that heat in. If you have a really, really good sweater, or you put another sweater on, your sweater is capturing more of your own heat. It's the same thing with our greenhouse gases. More greenhouse gases is just like putting another sweater on. You're trapping more heat inside. And that's where the problem is. These fossil fuels were storing carbon and keeping it out of our atmosphere, but we're just putting it back in. And that in and of itself, that act of that, carbon dioxide is not poisonous, but it is a greenhouse gas. It's thickening this greenhouse layer. Therefore, it is slowly warming our Earth. But again, this effect in general, very, very important. So go ahead and pause here and go check out this video. This video is a really good graphic overview of the greenhouse effect and also talks about greenhouse gases, why greenhouse gases work. Why do these gases hold in heat but not others? So pause here, take a look at this video, and then move on. So what are our greenhouse gases? Our atmosphere has tons and tons of different gases in it. That's what these two pie charts are showing. So here on the left, most of our gases in the atmosphere are nitrogen. This is in the form of N2. We also have oxygen, incredibly important for us as humans. Nitrogen and oxygen take up the majority of our atmosphere. 1% is, or 0.9% is argon, another gas, and 0.1% are trace gases, so other gases, but they're very, very small amounts. This red graph over here is those trace gases. Carbon dioxide makes up the majority of those gases. So although on this chart it looks like, wow, carbon dioxide 93%, that is 93% of this 0.1%. So there's not that much in the atmosphere. Methane and nitrous oxide, which I'll talk about more in a second, also make up our atmosphere and are also greenhouse gases. All these other gases are not greenhouse gases. They don't trap in heat. They're here in the atmosphere, but heat can just move right past them. But when heat, sees or runs into carbon dioxide can actually absorb that heat and shoot it back towards Earth. So the point is, we don't need that much. Yes, Earth needs greenhouse gases, but we don't need that much greenhouse gases. A very little bit, 0.1%, is all we need in order to warm up Earth to the appropriate temperature. This is even more crucial when it comes to humans releasing carbon dioxide, because we don't need that much as it is, and we're increasing that. We're saying, hey, we're just going to keep adding carbon dioxide and going to enhance that greenhouse effect. So the greenhouse gases in our atmosphere, it's very important to know this order. The first one is water vapor. And you're like, well, it's not even on this graph, because water vapor is more local. You don't really find it in our upper atmosphere because water vapor usually exists as clouds and in droplets in clouds. But it still acts as an important greenhouse gas. And you know this. You might not think of it, but you know this. When it is a humid day, what's humidity? Humidity is just water vapor. But that water vapor makes it feel even warmer. It'll say, oh, it's 80 degrees outside, but it feels like 90 because of how much water is in the air. But why are we not all crazy about, oh, water vapor, it's going to kill us all, like global warming? Because once you hit 100% humidity, that's it. The atmosphere can't hold more water. We can't really add water. Like if we add water, it would just turn into rain because the atmosphere just can't hold that much water to begin with. So that's why there's no crazy outburst of, well, water vapor's in the air. Why are we not complaining about it? It's because it caps out. The next highest greenhouse gas in our atmosphere is carbon dioxide, and you see that here in this graph. Carbon dioxide makes up the majority of our greenhouse gases. We also have methane. We'll talk about methane more when talking about climate change. And then also nitrous oxide. Nitrous oxide is also a laughing gas. But as you can see, a very small percentage is nitrous oxide. So definitely know these four and know the order of these four, especially water vapor, because it's kind of a trick. We don't really release water vapor, but it is the #1 most abundant greenhouse gas. This graph is showing the amount of carbon dioxide that is released, or I should say carbon dioxide equivalent. For example, methane is a greenhouse gas as well, but it's actually a lot stronger than carbon dioxide. It's a better greenhouse gas, so to speak. However, we just release a lot less of it. So looking at this graph, we're looking at time on the x-axis, and we're looking at the amount of carbon dioxide equivalents on the y-axis. So for example, methane right here, we actually don't release like tons of methane. It's just methane's a lot stronger, and that's why we put it in carbon dioxide equivalents. But here's the major thing I want you to get from this graph, is methane, for the most part, is the same as far as how much we release. It's not really changing over time. Nitrous oxides and these HFCs, which we won't talk too much about, but those aren't really changing either. The only greenhouse gas we're changing is this carbon dioxide. And we're releasing a lot of it, and it's getting worse. We're releasing more and more carbon dioxide. The other thing I want to share with you is the scale of this. These are emissions in million metric tons. Million metric tons. So this is saying in the year 1990, we released about 34,000 million metric tons. A metric ton is 2,000 pounds. So really, we're releasing 68,000, but this is million. So we're releasing, that is trillion, we're releasing 68 trillion pounds of carbon dioxide, and this is globally. So a ton of carbon dioxide. This isn't some superficial issue. Again, our atmosphere doesn't need that much greenhouse gases, but we are pumping tons and tons of greenhouse gases into the atmosphere. And that's where the worry comes from.